Adian Stoika, Vyasekar, and Aditya Kela, to just name a few. These are the faculty involved, and there are numerous students involved as well. Perhaps. Oh, great macros I have invading your entire network right now. No. Okay, so we all know that video is incredibly popular already. In terms of number of bytes, we're looking at. You want to just?
Yeah.
I think
I'll just do.
Okay, whenever you hear it, this is it. The manual audio-based communication channel. So, so we're looking, roughly sort of 70+% of all traffic, in a few years. And one of the key challenges that we see, next slide, is that we're relying on these CDNs to deliver all of this traffic. And we're already beginning to see the stress on these CDNs in a variety of ways. This is from not our own work, this is actually from a collaborator's piece of work in SIGCON 2012, looking at a variety of CDNs delivering traffic. And here they're talking about things like failed sessions, where failed sessions includes things where the client failed to actually get the video at all, but also includes sessions where the video quality was incredibly subpar. And so we can see that CDNs under stress, during high demand periods, often have very high percentages of what they call failed sessions. Next slide. And so in this talk, we're going to look at three things. We're going to look at what do we mean by good video? Oh, let's make better internet video. What does that even mean to us? Then we're going to look at sort of two other pieces of work that we've been doing. How do we improve the CDN delivery of voice over video on demand? And how do we improve the CDN delivery of live video? Next slide. Okay, so this is a high-level picture of the video ecosystem today. We have content providers of various types like ESPN and HBO. They're the ones making the shows, right? And while they make the shows, these are not really internet companies in any way. They rely on, CDNs of various types like Akamai and Limelight to deliver the video to their end consumers. And the end consumers watch this, and actually go ahead and click. And so the interesting thing about this entire ecosystem here is that, well, what happens? So HBO pays Akamai. They say, here, have some money to deliver this content. Akamai, in return, tries to do the best job they can to deliver the video to the users. And the users, one more click, basically end up watching if the video is good. If the video is very poor quality, the engagement gets dropped, and as a result, the content providers get less money because they're relying on advertising as part of their revenue mechanism. So, okay, let's try that. Yay! Okay. Okay. So this is the basic ecosystem that we have. This is very similar to the slide that were put up earlier about how does engagement produce money for Yahoo. Okay. So being an academic, what do? We say, oh look, video quality. This is an important problem. We have this vague description of a problem. We find a grad student that's very smart, and we say, make this video better. Right? And so, so I have a grad student. This is one of my grad students that works on this project. And I told her, and she's very happy at the beginning of this project, obviously, smiley, happy face. And I told her, let's go make the video better. I said, oh, you should talk to our collaborators as well. And so, here's Vyasekar. She goes to him and she says, hey, I need to make the video better. That's what Srini told me to do. How do I go about doing this? And he says, increase the bit rate. That'll make the video better. Right? Get a higher bit rate, better quality as a result, people will be happier. Now, he goes to Srini. Srini says, just ignore that. Now, the important thing is these buffering events. If I see a little dial on the screen, that means the video is not good quality. I don't care about the bit rate it's coming in at. It goes to Aditya and says, oh, it's not really important what bit rate you get, so long as you don't keep switching, because then people will complain that sessions, making sure everyone gets sort of a fair shake and then all the content providers will be happy and the users will be happy. And of course, promptly, the student becomes a little less happy. Yeah. What am I supposed to be doing? What does good video really mean? And so what we realize is that we don't really understand this. Despite a lot of people working on improving video for the internet, this concept of what is better and what is worse is actually incredibly vague when you talk to any two people working in this area. So what we did is we said, look, it's not really important, what each of us think is in terms of better. The key goal here is higher engagement. So we can really say if people in general like it, that means the video is better, right? And I think most of us can agree to that, especially in a corporate environment where you say, look, the important thing is higher engagement leads to more dollars, and that clearly is good, right? And so what we do is we said this is the quality of experience model. That we say, look, this is what people are actually experiencing. This is what the community as a consensus is saying is good quality. And why is this important? Well, we'll hear some more talks today about things like, let's reduce join time, let's reduce buffering rate. In any sort of system design, there are often trade-offs. So for example, if you're looking at things like bitrate adaptation algorithms, you might say, look, we're going to be very aggressive about increasing the bitrate, but the end result is that you'll get maybe higher quality, and that may sound good to you in terms of the average PSNR, or video quality index, but you're at a higher risk of buffering events. So there might be these trade-offs involved where you say, I can improve one thing, but at the cost of something else. And you have to evaluate those trade-offs very carefully in deciding whether this really will make people broadly more happy. Picking a different server, comparing different CDNs in a really quantitative way. Well, these are all things that this quality of experience model could help you, infer or quantify. Okay, now we're not the first people to have thought of this, right? If you think about things like audio compression formats, video compression formats, the HCI community has done this for years. What do? They say, look, I'm going to take something like MPEG-4, and it has these great little tuning knobs that say, quality. And they have a very clear way where they say, look, if you tune this knob in the following way, this is what people will think of the encoded video on the Blu-ray disc, right? And so they have a clear sense of what the trade-offs are involved in terms of mapping things that are objective scores in video coding or audio coding to what are mean opinion scores of people. So that's been done in HCI for a while. Well, how do they go about doing this? Well, they take a group of us, like here. They say, look, I'm going to make you all watch Batman. You're going to watch Batman for half an hour, and then I'm going to show you a different version of Batman, right? And all I'm going to do is I'm going to change some of the video encoding parameters, and then you're going to tell me which one did you like better and by how much. So they take surveys. And so when you have a simple linear metric, you can do this quite effectively. And you say, look, this is how this encoding metric converted to this opinion score. Right? So we have these user level studies, but there's some problems with this. Well, one, it's not really in the wild experience, right? So the catch is that people sitting in a room often will have sort of maybe perhaps a slightly different judgment than people sitting on laptops watching YouTube videos or Netflix or Hulu, right? So there's sort of an aspect of that. We're going to take a more captive audience. The other problem is that when we look at these sort of metrics, well, we can basically sort of vary one thing. Now, what they typically vary is the encoding quality. But if you look at the internet, when we talk about delivery quality, there's a huge number of parameters involved. There's things like the buffering rate, the overall buffering ratio. There's how often you switch bit rate. What is your average bit rate? What are sort of the drop frames, right? So there's a bunch of things that may occur in terms of video delivery, and we now have a little bit of a combinatorial explosion. Right? I can't just say, look, you're going to get parameter set A, you're going to get parameter set B. Well, if I have 6 or 7 parameters, and I had to search through this whole space, I'm going to be doing user studies till, the cows come home, right? So it's going to take a long, long time to do that type of approach. Okay, so what are the metrics that we're really worried about? Well, if you think about video, there's a few that immediately come to mind. One is join time. So when you first start up a video, how long does it get off the screen that says starting video? Another important one is buffering. So how often do you see the little spinning dial which says, oh, video's not there yet, please wait, and how long it is. So it may be that you can make a trade-off. You can say, I'm going to buffer for 1 second every 5 seconds, or you can say, I'm going to buffer for 20 seconds at the end of every 5 minutes, right? So, both the rate of buffering and the overall ratio are important. And then in terms of things like the actual bit rate, if you look at most internet video players today, they have a little quality bar of some form or an HD button or something like that that sort of increases over time based on what it thinks is the available bandwidth on the system. And then it'll say, oh, look, I think you have enough bandwidth that you can go up to the next quality level or next resolution or the next encoding level. And so they'll do that, and they'll do this automatically. Now, the caveat is that whenever you see this change, you'll see sort of a jump in quality or a decrease in quality of some form, which may be a little bit jarring if they don't do a good job of it. And then there's the average quality as well. How close am I to the sort of cutting edge envelope of the best quality I can deliver, or do I play it a bit more conservative in order to avoid things like buffering? So here are some of the key parameters. And so going back to this picture, what do I do? Well, the first thing is these subjective scores, these mean opinion scores. Now, we're going to take a slightly different approach. Instead of putting people into user studies, we're going to say, look, people are watching these videos all the time. So we're going to take a big data approach. We're going to say, look, we have huge amounts of traces. In our case, this was kindly provided from a company called Conviva that provide video for companies like ABC and ESPN. It's a company that Hui Zhang and Ian Stoika started. Also, we have some nice big data type approach of showing us what does video look like, how long do people watch. So we already see the engagement, and engagement is what we care about. So we're going to replace this, on the top side, we're going to replace this with engagement. That's what we really want to predict. And on this side, now we got to figure out, okay, what am I going to put here instead? We don't want to use PSNR. That doesn't really have to do with internet delivery. What do I put there instead? So you could put the buffering ratio, you could put the average bit rate. The question is, it's going to be some combination of these, actually. So this is actually going to be a function of all of these, and I had to figure out what this function is that is predictive of the engagement. And that's the core goal of our study. And we can figure out what this function is, and we can figure out what this relationship is, and can we predict how long people will watch any particular video based on the delivery quality we give them. So then it opens up a whole path of different optimization strategies that we could possibly do. Okay. And for anything that we don't really understand well, what do? We throw machine learning at it. We say, we don't understand this problem exactly. Maybe the computers can figure it out. All I have to do is throw enough data at the problem and hope that things work out. And so what do? We have these big traces. And in these traces, they say, oh, Srini watched, I don't know, the Olympics for 3 hours last night. Okay, oh, that's great. So we have things like engagement. And they can say, oh, look, the quality at which, the Olympics was streamed to Srini was the following. He got an average bit rate up 2 megabits per second. Oh, it buffered 10 times. And so we have a whole collection of these. Oh, but Srini only watched it for an hour and a half the previous night, and the quality was much worse, right? So from that, we hope to apply the appropriate type of machine learning and output this predictive model. And the important thing about this predictive model is it also has to be actionable in some sense. It can't just be, I magically get a relationship and a prediction. Hopefully what we want to be able to do at the end is tune something in the system where I say, if I make this better, this will clearly get higher in terms of the predicted engagement. Okay. Now, so what we did was we did this. We actually just threw the data into machine learning. We tried a couple different machine learning algorithms. We picked them a little bit intelligently because we knew certain properties of the data. It turns out that if you look at these sort of relationships, some of them are very threshold driven, some of them are non-monotonic. There's some oddities to the types of relationships that you see, at least individually, between engagement and quality. So in the end, what we realized is that decision trees fit best to the type of problem that we felt. But the accuracy was terrible still. So we were basically within sort of 10% prediction of the engagement about 40% of the time. This is not very, a very desirable result. So then we started thinking, what's going wrong? What we realized was that there were a number of confounding factors in this whole study. We were throwing data willy-nilly at machine learning and hoping that it would sort of tease out the entire relationship somehow. But there were lots of sort of hidden labels in this data set that were actually quite important. So for example, we threw the entire trace at it, but realistically there was live streams that people were watching and video on demand streams that people were watching. And inherently the behavior of users when they're watching video on demand versus live events is very different. So here's a CDF of simply the engagement of users for both live and VOD. So one thing you'll notice is, so live, people watch some portion of it, it follows some general distribution. But if you look at VOD, there's this big chunk over here where a large percentage of users watch the entire show. But why do you think that's true? Anyone know? Anyone have any conjectures?
Because you're watching what you like.
One, you're probably watching what you like in the live also. But the thing is that VOD, the big advantage of VOD is when you want. So it's not just what you like, but it's when you're free. When you're watching the Super Bowl, if you say, I only have an hour free on Sunday, January 30th or whatever, well, you'll watch it for that hour and then you'll go do your chores. VOD, you'll say, oh no, I'm just going to wait a week and I'll watch it then, right? So one thing is that VOD is inherently much more reschedulable, right? And so this is purely conjecture and anecdote, right? So, but people have different viewing patterns for different types of recorded shows. The similar thing is true about connectivity. So if we look at this general relationship between quality and engagement, people's expectations have a lot to do with it. So it turns out if you train people to say, look, I'm going to show you bad junky video for days on end, they will happily become accepting of bad junky video, right? And assume that that's what the way it is, right? If you think about 10 years ago, you said, oh look, I'll give you a postage stamp size video. You should be happy with it. We were happy with it, and we would watch the little postage stamp videos for hours or whatever in 2000. Now, if you see a postage stamp video, you're like, oh dear God, let me go off the site, right? So people's expectations change over time, and they're trained by the environment. And so if you think about connectivity, people know connectivity plays a role, right? So going back to our talks earlier, when you see 2 bars in the top right corner of your phone, you expect things to be bad, right? And then when the website loads slowly, you say, oh, it's just the AT&T, Verizon, whatever network, it's not, I should wait. So we have the same behavior here. If you look at things like DSL, cable, other connectivity, wired connectivity, versus looking at wireless connectivity users, purely by looking at their IP address and ISP, we see very different tolerance to buffering, right? So what ends up happening is, DSL providers are much less tolerant of buffering. They expect, performance to be good. Wireless users say, oh, this must be the cellular network. They're much more tolerant. And, there are other effects that are in here as well. So you can't just throw this data at, machine learning and hope for it to tease this all apart. You at least have to include these particular labels in some fashion. And there are more, right? So there's not just type of video and connectivity. There's the type of device you're using, right? So if you're watching on a phone versus a TV versus a laptop, you have different expectations. There might be location that you're at. The popularity of the show might make a difference. Maybe it's a very popular show, people stick with it. Might be time of day effects. Maybe people, when they're at work, watch for a few minutes, quickly realize someone else is expecting them, and then tune off. Maybe during the evenings, they're happy to watch for hours on end. Or day of the week in a similar fashion as well. So these are all factors that might be in the labels of the data that we have to worry about. And so what we need is a systematic way of saying, does this really make a difference? Is this label really that valuable? And how do we incorporate them into the sort of the machine learning model that we're looking at? So, I won't go into too much detail. We actually analyzed these particular properties, and we had a variety of statistical tests, and we, in particular, identified these red ones as truly confounding factors. That you have to consider the type of video, you have to consider the type of device, you have to consider the connectivity and the time of day in terms of how people watch video in some way. Okay, so now we've got to figure out, these are the confounding factors. How do we incorporate them into our prediction system? So we could just take machine learning, add another extra label to the data, and say this is machine learning's problem. Solve this, build me an appropriate decision tree, and predict the output quality. Now the problem here is that if you look at the output decision tree, now it's going to have all these strange labels all over the place in the decision tree, and it's going to be a little bit more complicated, the decision tree, in terms of making sort of actionable decisions in terms of system priorities, resource allocation, or anything like that. I'm going to have a much harder job of that. But maybe this will work okay. Also, machine learning might be, not be able to tease apart these sort of other labels as effectively. The other choice is partition the data set. You take sort of, each of the sort of independent sort of settings that you have. You split them into different data sets. You train your machine learning model independently on each one. The problem here, of course, is sort of dimensionality, or sort of, combinatorial explosion. If you have a lot of these, you're going to have a lot of different models. But the nice thing is that for any given user that shows up on your system, you say, oh, is this a mobile user? Is he using a TV? You can match it very quickly to the appropriate model, and then you have maybe an accurate sort of QoE model that predicts what their behavior is going to be. Now, in practice, what do we find? We find that splitting the data worked more effectively for us in a wide range of situations. And so this is actually what we go with. So we go with this approach in the end. And the key thing is that after going with this approach, well, what does our end data really look like? Now we're up at the 70% level. So we have a 70% accuracy in terms of predicting your, the percentage of a video you're going to watch within 10%. Okay? And so now we're at least getting into the realm of possibility of saying, look, I can do clever system optimizations based on the predictions of how much video you're going to watch. Now you should realize that this is a lower bound, right? We just took in a couple key factors, right? Once you add maybe things like personalization, maybe you look at some other factors, you can actually probably do a much better job of it. This is simply a proof of concept in some ways. Now the other important aspect is, actually I'll leave it at that. So we think we can do better than this, but we think this is already at the level where you can do useful sort of things. In fact, one of the things we did do was we looked at some trace data to try to figure out, even at this prediction level, can we do better jobs of allocating resources in a very sort of simple simulation? And we believe that we can improve sort of engagement broadly on a sort of a simulated CDN environment by about 20%. And so just to summarize sort of this part of the talk, can we evaluate sort of how effective a system is at delivering video using sort of just by observing user behavior? Well, yeah, we think we can. And the key challenge is overcoming these confounding factors. And it turns out there are some very complicated relationships between the quality of delivery and engagement. And getting the right sort of machine learning involved there is a little bit tricky as well. And so right now, what do? We produce a collection of decision trees that help you predict the type of engagement you could expect from a particular delivery of video. Okay. So that's kind of the first part of the talk. Now, what I'm going to talk about in the rest of the talk is looking at, okay, we've been doing this for a prediction. We don't have it directly applied in the other two, but the CDNs are the ones that are responsible for the actual delivery. How do we go about managing their resources effectively? And what other factors think they want to consider beyond just the quality of engagement or quality of experience? Okay. So first we'll look at the more simple video on demand type scenarios. And this was also brought up a bit earlier in today. If you look at the CDN market, there are two things that people have been talking about to get CDNs to operate better, scale better, perform better, or are just general market trends. So one is that CDNs are looking at P2P CDN hybrids. One of the key problems in CDNs is that when this demand goes up dramatically, they can't just magically add CDN nodes very quickly. But the one resource that does scale with demand is the number of peers or clients out there. Can we leverage some of those resources to make their delivery scale? So, two popular things that you may have seen. Akamai Net Session does P2P in order to do delivering of content. And China Cache Livesky is another system that leverages P2P as well. Another common thing that we're seeing out there, sort of an industry trend, is federated CDNs, either in the mobile market or ISPs in general trying to sort of get into the CDN marketplace as well. And so we have these sort of big data traces. Are there anything that we can glean from this big data that will help us understand whether these designs might work and how? So this is viewing behavior for, I'm trying to remember the show. I can't remember the show name. So this is a popular, I think, ABC show. And with most TV shows on things like Hulu or ABC.com, well, what happens? Every week they release a show. And then, a few weeks later, maybe 3 or 4 weeks later, they expire the show off their system. And what you see here is the number of viewers versus day from the beginning of this trace. And one thing you'll notice is that, here's episode 1. The first episode of the season gets released. Everyone goes and watches it right away, right? Because the cool thing is to be able to go to work the next day and say, hey, did you see Lost last night? It was really awesome. You want to be able to talk to your friends. There's a social aspect to it. Lots of people watch on the first day to be involved, right? We see the standard diurnal pattern, but you see a decay, and then when the next episode comes out, everyone wants to watch only the newest episode, so this one takes a big dive, and then the next episode is very popular for that first day. And so we see that very popular first day. If you look at it, probably an hourly range, it's probably prime time, 8 o'clock, whenever the prime viewing hours are, for the U.S. household. So one interesting thing about VOD is that when people said, let's use P2P type techniques for video delivery, almost always they're talking about live video. The reason is that in order to be able to use P2P, someone else has to be watching at the same time, right? And so the conventional wisdom is live video, use P2P, video on demand, that's not going to work. But the interesting thing here is, if you look at the first day, there's a lot of synchronous behavior. People are going home, they're watching that show almost a concurrent way, especially during that popular first day. So if you just look at the number of people watching the same segment during the same 5 minutes, during the same ISP, there's actually a lot of opportunity to leverage P2P resources. And that's what we found. I guess that got reversed. So conventional wisdom, P2P only works for live. Yeah, maybe not so much from our traces. Now, another interesting thing is about early quitters and sort of viewing demand on a particular video. So if you imagine a typical show and a typical user, historically we've been channel surfers as a community. You watch shows, you flip through channels, you see for a few seconds, it's no good, you go on to the next one. Maybe some of this has changed a little bit with online video. You see previews of this a bit more. The key thing here is that if you look at video on demand, once again, we see lots of people watch the whole video because they plan ahead. But for both live and video on demand, we see lots of early quitters, right? And so one interesting thing you would want to do in the system if you want to protect your core server resources is you want to get rid of these people, right? And so the right thing to do perhaps, historically I think people have said, we'll build a system, you join the server, we'll coordinate and we'll interact you into some P2P cloud for delivery. Well, you should do the opposite. You should send these people to P2P right away. Start with them on P2P. Hopefully they'll just quit and go away anyway. And only the people that are really persistent should get the good server resources that make them engaged. Okay. Another sort of interesting trend that we saw that impacts CDN design, and especially federated design, is regional interest. So it turns out that, so if you look at sporting events, let's think about, March Madness, NCAA basketball. Round one, some little town in, the middle of Indiana, some college is playing in round one. Hardly anyone knows about it. Most people don't watch. But in Indiana, it's big news, right? Everyone watches that game. So here we have two graphs. This is looking at the correlation of the population of a region versus the number of viewers, right? So the region is bigger and the viewership goes up, we'll see a correlation of 1. And so for typical stuff, we see a correlation close to 1. Places that are more populous have more viewers. But then we have a whole collection of highly regional content, where only people within a small area of the country are effectively watching. And so when we have things like federated VDNs that have localized coverage, this may actually make a lot of sense. Like, how am I doing on time? A few more minutes? Okay. So we'll skip this one. And so, VOD CDN, so there's some, there are a lot of sort of interesting sort of details out there in the actual workloads that you can use to optimize how these CDNs operate. And so the last part of the talk I want to touch, this is work that's been going on for a while. This is actually work that's current. So this is a little bit rough, okay? So this is unpublished, raw, stuff. So live video, So live video is very different than video on demand. You can't really leverage things like caching very effectively in order to do things like the delivery and make the delivery efficient and high quality. But if you look at live video on the internet today, we talk about big events like the inauguration. We say, 7 million viewers. But you talk about things like live video in the real world. We talk about things like the Super Bowl. We're talking hundreds of millions of viewers. So the potential for increase in sort of demand for live video on the internet is actually enormous, right? So there's a big gap between these numbers, and so there's a big possibility here. Now, if you look at CDNs today, CDNs were really developed for web content delivery. They got subverted into video content delivery because video became the dominant source of bytes on the internet, but they're not really that optimized in many ways for live content delivery. They've been sort of reused for that purpose. So what do they do today? So this is a sort of a rough sketch of what Akamai does. We have two different videos here that are being delivered. They have video sources for the two different channels. They divide all the CDN sort of points of presence into these clusters. They have interior cluster nodes for delivery, and they have edge clusters where the clients connect to. These edge clusters, there are thousands of these. Interior clusters, not as many. Now, video requests come in at these edges from the clients. And the key thing is that what they do is that they try to pick the best interior cluster that's a match. And this goes up to the video sources. And effectively, the data responses come down in sort of this tree-like fashion. And so this is a distribution tree. So they look at all the requests coming up, and they effectively build up a distribution tree for the content. And so this is kind of like multicast on the cheap, right? Let's build a multicast distribution tree purely based on the requests themselves. And building this tree is sort of a key optimization problem for these CDNs in terms of delivering live content. You don't want these interior nodes to get overloaded, and that's really sort of the bottleneck. Now, one important thing is that if you had a global view of all this demand, you can actually do very smart traffic engineering. And I'm not going to go through it for lack of time, but you imagine if you have two different sets of channels, you have some topology, you can figure out a better mapping if you could see the whole thing and then optimize. And so you can probably figure out, the blue channel should go on the left, the red channel should go on the right. This will ensure that they both get a reasonable quality video in the end, rather than overlapping in some way like this. Or one node grabbing the resource first, making nothing available for the second channel. And so, doing sort of resource allocation, one important thing is that usually these channels are available at multiple bit rates. So it's not that you only are picking a particular path through your network, you're also picking a bit rate for each hop along the path. So you have to remember these two problems are very closely linked. Okay? Now, the problem with going to the centralized control is that centralized control, we've all heard sort of the software-defined networks, centralized control, bandwagon, centralized control is great. It's actually pretty good for things like data centers, but once you put it onto something like a CDN, you're dealing with something that's vastly larger, right, in terms of geographic scope. And so when you have things that are like localized changes, like congestion occurs on some link, getting this information to propagate to some centralized controller, getting a new set of sort of forwarding tables for all the nodes along the path takes a lot of time. And so what you want here is local control, which is what Akamai does today, is actually far more effective in certain ways in terms of reacting to these types of transient events. And once you add sort of multiple controllers for scalability, you deal with things like network partitions between the controllers and the end nodes, going down the centralized control path is actually very daunting. So what we've been doing, so this is, like I said, early work, we've been going down what's called a hybrid approach. We want a centralized controller that does sort of very rough planning in terms of topology and forwarding tables and configures these things across all these nodes. But we want a local control that reacts to events like client joins and leaves, as well as congestion events. Now the big problem whenever you say the word hybrid, though, in this type of situation is how these two things coexist in any way. And so this is what we're talking about, just to clarify what we mean by sort of hybrid control. We're going to have these interior clusters that are doing sort of the delivery. These are the clusters I mentioned earlier on. We have a centralized controller. Each of these nodes, so the global controller is running, this controller is running global discovery. He's figuring out which nodes, which clients are connecting to which clusters, and so where is their demand? What are the resources available? These local agents are looking at local changes in connectivity and demand. And what they're doing is that, within each cluster, we are running Apache to do forwarding of these live streams. We're building a little forwarding table within Apache to forward it in the right direction. So just to give you a slightly higher level, so what goes up to the global controller? Kind of a demand matrix. So here's the people that want it, and here's the topology of the network. Here are the link bandwidths. What they output are distribution trees. So they output a distribution tree that you want to actually forward on. And this is basically how you would like the system to operate. This will give you good performance. But things change over time. Whenever something changes, just local discovery, local control can modify the forwarding table as necessary. Okay? So does this work? Well, this is, like I said, early results. So this is actually a simulation of a topology that looks like Akamai with a large number of video channels and a large number of clusters involved. So we're looking at sort of thousands of distribution clusters and hundreds of video channels across them. These two schemes are simply sort of greedy algorithms of various types. So this is very similar to what Akamai does right now. And we believe by going to a little bit more of a centralized control, we can actually improve the bandwidth allocation by about sort of 2x. So this is the sum of the quality of the delivered video across all clusters. Now, one important thing, this point was made earlier, shouldn't just look at averages, you should look at the sort of outliers as well. I don't have the graph here, but we have looked at the outliers as well. And this actually is quite a bit better in terms of avoiding users that get no video. Just a couple minutes. Okay, so the other aspect is responsiveness. So we wanted to get the benefit of local control for responsiveness of adding new channels, adding new users. This is basically a graph that shows you, this is actual implementation. So this is actually running on Amazon EC2 with an external controller at CMU. And so as a result, the scale is quite a bit less because now we have to pay dollars to get Amazon EC2 time. And so the scale is smaller, and the number of nodes as well as number of channels is much smaller. But what we see is that we can have users and channels join our system at sort of sub-second type time scales. Okay? So that's pretty much, so if you look at the type of work we're doing, you can read up the details of some of this work. What is good video? This was in CCOM 2013. If you look at the video on demand delivery measurements, this was in IMC 2013. And right now we're working on the live video, and this is work in progress that we're looking at. Couple other points for people that are interested in video or in understanding internet performance. One is in CONEX 2013, we looked at how do we develop URLs that are a little bit more optimized for multimedia. These are called information-based references. One of the problems with multimedia URLs in general is that they typically reference a particular file. So you can say, oh, here's a Srini.jpg or Srini.mpeg. You put this in a URL and you embed that in your web page. But if your client doesn't want to use MPEG or wants to use a different file format or a different resolution, this is a very common thing we do with multimedia. But the URL format really is very file-centric. And so we sometimes hide this in various ways and through various hacks. And so this is a proposal for saying, look, this should be a first-class entity. How do we change the types of URLs we use to be both supportive of different formats, different resolutions, and different quality? This helps you, port across devices, port across network conditions, and across device capabilities of various types. The other sort of interesting work that we're doing in this area is starting to look at this notion of quality of experience for something beyond video. So in particular, we're starting to look at it for mobile web browsing. Is there a way we can look at mobile web browsing behavior and traces to figure out how happy users are? Can we apply the sort of same concept we applied in the video context to this? It turns out this is fundamentally much more complicated. Video, there's only one kind of behavior. You have a 20-minute video, and I say, how long were you there? Now, every web page is very different. Some web pages, yes, you're supposed to click through 20 web pages, and maybe the number of click-throughs you have really represent how happy you are. Maybe for some other web page, that's not the right metric. So getting a metric for how happy is the user directly from the type of web page or from network observations, it's actually quite a bit more difficult. And also the type of sort of network parameters that are involved here, especially in the wireless networks, is also much more varied. And so this is an opportunity for us to try to extend this methodology a bit further. That actually brings me to the end of my talk. And, thank you.
Time for a few questions?
Okay, sure. I may have missed this, but how did you control for early lever? I mean, because this is how I use video sites. Is you go to watch a video, and then you maybe watch it, and then maybe you watch 10 seconds of a view. It's the poster frame looked interesting, but whatever. You just really wasn't any
So for the QoE stuff, we actually just filtered out early quitters for that purpose. The ones that watched it purely from a perusal perspective, because what we wanted to be able to see was the observation of network delivery effects and their impact on observation.
Okay, so at some threshold or percentage, you say, okay, we think that you actually do want to watch this.
Yeah.
Your intention is to watch it.
Yeah.
Okay. And the second question is, in the VDN work, does it matter if I'm doing, partial download or full download versus RT, SP or HLS, or does that have any bearing on that work at all, or is there a relationship between the kind of benefits you can get with the work you're doing in VDN?
So here we largely assume sort of a chunk-based live download. So we're using sort of HTTP chunking, based live delivery. As far as sort of the core assumptions of the work, would it be hard to map it up? So the caveat that it probably played a role in, so the core of the system is this sort of ILP that then gets approximated in various ways in order to figure out what the appropriate routes are. I'd have to go through and think about the ILP and see, does there any difference in sort of formulation? I don't think offhand that there would be at first glance, or in the 5 seconds I have to answer the question, but I can't say for sure.
Not off the top of your head, but possibly.
Yes.
Okay, cool. Thank you.
Sure. Oops, wait.